Hello, so today we are going to do this problem which is part of Leetcode daily challenge, house robber. So what this problem says is we have a professional robber who is planning to rob a list of houses along a street, and each house has some amount of money, but our only constraint is that we can't rob adjacent houses, right? So let's say this is a street, this is first house, second house, third house, and then fourth house. The robber can't rob this one and this one, right? Because then that will automatically, you can imagine, trigger security system or something like that. So they would have to, if they rob this one, they would have to rob this one, and then that's it. If they rob this one, they would have to rob this one. And so given an array that represents these houses and the amount of money in them, we want to return the max amount of money you can rob tonight. You can rob from these houses without, of course, like triggering these systems. So basically the max we can get without taking two adjacent values, right? So that's pretty much it. So for example here, well, you could do 1 plus 3, that would be 4, or 2 and 1, that would be 3. So better get 4, right? So that's the idea. In terms of numbers, the length is not too big, it's just 100. So let's see how we can solve it. Okay, so let's see how we can solve this. So we have a list of, let's say take the first example, 2, 3, 1. Maybe let's just add more things. Let's say 4, 6, something like 1, 8, right? So if we take these, right, 2, 3, let's say this one, 1, 4, 6, 1, 8. So we only have two options, right? We only have two options. It's always better to continue going as long as possible, right? Because we are guaranteed that all numbers are positive. There is no negative number. So if we start here, we would have to do something like this, and then do something like this, and then that's it. Or you could still start like here, and you could skip 2. You don't have to skip 1. So you could still do like this, but maybe do something like this, and then do something like this. That's entirely possible. Maybe that's even the max. Same thing, if you start here, you could do here, but you could also just jump straight to 8, right? Let's say if those were just 1s, that actually would be optimal. So that's the idea. So what does this mean? This means basically that at each, for example, at this one here, right, we have multiple options. We can go to 3, we can go to 1 here, we can go to 4, we can go to 6, we can go to 1, and we can go to 8, right? You could do something like 1 to 3, 1 to 1, 1 to 4, 1 to 6, right? So as long as you don't violate the condition of 2, and then from each one of them you still have the same thing, as long as you don't violate the condition of ones that are next to each other. Okay, so this actually lends itself very easily to a recursive approach, and one with memoization, because we might get to multiple state multiple times. So for example, you may go from 1 to 3, like this. So you may go from 1 to 3, and then from 3 you may go to 4, or you may go from 1 straightly to 4. In both cases you arrive at 4. Going from 4 to 8, getting that max, it's the same procedure. So we shouldn't do it multiple times for each of these two paths. So that's where we should memorize and keep the result each time in a map or something to save it for usage later, right? So that's the idea. Now, how do we recurse? Well, let's call our function maybe that we will use, let's call it maybe, I don't know, rob. Yeah, rob makes sense. At position I, right? So here, position is 0. When we are here, I is equal to 3, right? So at each time, we have only two choices, right? We can either grab let's call the array here A, right? If we decide to grab the element at this position, then we have to start trying to start trying to grab the not the adjacent one, the one after the adjacent one, because we can't do I plus 1 once we take I. So we can only start from I plus 2. So maybe grab it and maybe leave it, right? Because we may take this one, or we may just jump past it, right? So this would be helper, call it rab of I plus 2. Okay. What is the other choice? The other choice is to decide, okay, I'm not going to rob this house. It may not be because it's adjacent. It may be just because it's better to rob maybe 4 so that you can get a chance to rob 8, right? But we will try all of them. This is trying all of them, right? So here we would do a rob of I plus 1, which means basically just go and try starting from I plus 1. Okay, so maybe skip 1 here and just go try to rob from I plus 1, right? But we also try to rob 1, so we do the 2 possible choices and we just take the max of these 2. So that's the main idea here. But of course, since we are, and this is what we need to return, and at any given point you only have these 2 choices, because when you call rob I plus 1, you would either take it or skip it again. So every time you will explore all the choices, because every time you recurse and decide to take it or not take it, right? And so here we just need to do our base case, which is when I is equal to the length of numbers. So we are done. In that case, there is nothing to do anymore, so we just return 0. Okay. And we sorry, actually here we return the max each time, right? And since we add, this would get us the sum because of this adding here. We take the element, we add whatever we get from before, and so each time we'll add the sum. We'll add the number that we get, or the money that we get. Yeah, so that's the idea with the recursive solution. We can do the same thing with the dynamic programming solution, actually. So with dynamic programming, we just need to define our state, right? So let's say dp of I is how much money robbed so far at house I. Okay. And so we just need to represent a recurrence relation for that. So what would be the recurrence relation there? So we can actually just take inspiration from this, right? So when you are at position I, right, it's either that you don't take this house, you don't take the house at position I, right? And then in that case, you are allowed to take the one at position I minus 1, right? Or whatever was the max at position I minus 1, maybe we skipped I minus 1 and took the one before, right? And so that would be dp of I minus 1. And then the second option is taking the value at I, but then in that case, you can't take at I minus 1. You take the one before, because we can't take adjacent one, so dp of I minus 2. Okay, so that would be our recurrence relation. Now, since we are doing I minus 2 here, to get correct indices, we have to pre-calculate for dp of 0 and dp of 1. So what is dp of 0? So dp of 0 is actually just should be just a of 0, right? It's just the max of a of 0 or nothing, so just a of 0, right? What is dp of 1? That's just the max, right, of a of 0 and a of 1, right? Yeah, when you are at position 1 here, you can either take this one or this one. You have no other option. 0 is not the max because those are positive values, right? So that's the idea. And so we could just use this formula here to build our dp recurrence, and then the result that we want to return is the last one. Okay, so let's implement the 2 solutions we've seen so far. So the first one is the recursive one, and so we need a helper at position I, right? And our base case is when we reach the end. Let's just rename this to A, it's easier to write. Then we want to return 0, otherwise we have 2 choices. Either take the current I, but then in that case you would have to skip the previous one. You have to skip the next one, or just take the next one and don't take the current one, or at least go explore starting from the next one. And so here we return this, and then we need to call our base case with indices 0, and we have two options: start from first one or start from the next one, right? And so the max of these two. Okay. Now one thing we need to do here is memorize the result. As I said, you may arrive at one position from multiple places, but you want to calculate the optimal value from that position only once. So we want to memorize so we don't recalculate. And so how do we do that? We can just have a map, something like this. And here we check if I is in memo, right? We just return. If we already calculated it, we just return it. And here, when we calculate, we save it. Okay? And then at the end, just return it. Okay? And so that's what we'll use here. Okay, so this is because, well, sometimes because of this I+2, we might go past the length by 1. So this alone won't catch it. So we need bigger or equal here. So yeah, let's run this again. Looks good. Let's submit. And that passes, right? Okay, so actually in Python you could do it easier than creating the memo yourself. In other languages you probably have to create this hash map yourself, but in Python you could just there is a cache annotation that you can use, so we'll just use NLRU cache, and that should work as well. And that works, right? Cool, so we explored the recursive version. Now let's do the DP version that we said in the overview. So we said that our recurrence relation would be DP of I-1, and then the max of that, and I-2, right? So this is our recurrence relation. So what we need is, we definitely need to check, we definitely need to initialize our DP. So let's initialize it to just zeros. And here we need the length of A, of course. And we need since we depend on I-2 here, we need to initialize 0 and 1, right? Because otherwise this won't work. It will give us a negative index. So for DP of 0, it's just, there's only one possibility. For DP of 1, there are two possibilities. We can either take this one or take this one, but we can't take the two because they are adjacent. Okay, so now we can just create our we do our recurrence, right? So we start from 2 because so this would be 0. We can do 1, and we already calculated 1, right? So we do 2 to the length of A, and we just use this recurrence relation. We build it up, right? And then at the end, we want to return the last element of DP because that's the max. And so we just do DP minus 1 like this. Now there is only one thing here, is what if the array has length 1? Then this here won't work, right? So we want to just check that. So if length of I is equal to 1, we want to return only A of 0, right? So let's run this and let's submit, and this works as well, right? In terms of time complexity, this is O of n, and in terms of space, it's also O of n space because of this DP, right? But we can make it better because we don't need the entire DP array. We can make the space complexity better because we don't need the entire DP list. We only need the previous one and the one before the previous one, right? That's the only thing we need, right? So instead of doing the entire array, let's just have the previous. We need the current one, which is this DP of I. We need to fill that one. And we need now, which is the current one, or let's call it current. And we need the before previous, which is this one, right? So let's call it before previous. And all of them can be starting initialized from 0. That's what we did. And we don't need actually this. And here we'll just start from I in A instead of doing this. Yeah, we can also, let's do this for now. But we don't need this. So what is this? This is now. What is this? This is the previous. And this is the before previous. Okay. Now we just need to make sure we assign these values correctly for each iteration, because we no longer have a table. We have we alternate in one variable, right? And then here we return, this is the current actually, and here we want to return the current, right? Because that's the latest one. So here we just need to make sure that prev is the current from the previous iteration, right? So prev is the current value from previous iteration, right? And when we do this, also we want the before prev to be the prev from the previous iteration, right? So we can also decide to do it here. So before prev is the prev from the previous iteration. Yeah, so the before prev, right, is prev from the previous iteration. So that's why we initialize it here. You could also decide to do it after this one, like here. But both should work fine, right? Because both will get executed before this, and that's what matters. Right, and so here we can just change, since we only need a of I, we can change this to this, right? Okay, and that's pretty much it. So this is a, and that's pretty much it. This should work. So we replaced an array with only variables because we only need two places of the array at each iteration, right? So if we run this, submit, it passes, right? Now in terms of time complexity, this is still O of n time, but in terms of space, it's O of 1. It's no longer O of n, so it's a better solution. Yeah, so that's pretty much it for this problem. Please like and subscribe, and see you on the next one. Bye.